Monosaccharides can also be drawn in a different projection. This projection reflects the ability of the monosaccharide to create a cyclic structure and essentially creating a hemiacetal functional group at the same time. So what I'm going to show you now is how to take your Fisher projection and convert it to a Haworth projection. To begin with, we are going to number our Fisher projection, starting at the top and going down. Okay, now we're going to curl up the Fisher projection into what looks like a cyclic structure, but it's not quite created that bond or the hemiacetal functional group. As you could see at position 1, we still have the what should be a ketone right there, or sorry, aldehyde right there. So we start off 1 there, 2, 3, 4, 5, and the last one is 6 up here. So essentially this OH right here on the 5th carbon is this OH sitting right there. And it's going to react and create the hemiacetal with this aldehyde. So the reaction occurs, and when you create this cyclic structure, it's going to generate a new chiral center. That chiral center will be right here. In the notes, I talk about an anomer. This is a anomeric carbon, and anomers are when you generate a chiral center where there was none before. Because there's no blocking or anything getting in the way, we can create both anomers through this process. If the OH is facing up from the ring, like it is in this conformation, it will be beta, and if it's facing down, like in this conformation, it will be alpha. What you will notice is the OH groups throughout the rest of the ring at position 2, 3, and 4 are all similar position, 2, 3, and 4. So at 2, they're both down, at 3, they're both up, and at 4, they're both down. So these two Haworth projections I've just drawn are for glucose. They are just two different anomers. So this one on the left is beta D-glucose, and this one on the right is an alpha D-glucose. Okay, now if you know how to draw the Haworth projection for the glucose molecule, you should be able to figure out the Haworth projections for other monosaccharides. Let's take a look. Okay, so once again, I have D-glucose, and I am turning it into the Haworth projection from the Fisher projection. Again, position 2 is down, position 3 is up, position 4 is down. Okay, and it just so happens I'm doing a beta of the anomer. I'm going to keep it consistent with that beta right now. It doesn't matter, you could do it with alpha or beta right now. So for the next molecule, we're looking at D-galactose. D-galactose, again, is a 6-chain monomer. Okay, it has the aldehyde on top. It's essentially the same looking structure, except the OH in certain positions is changed. Okay, so let's take a look. We have 2, 3, and 4. So if the OH is on the right side at position 2, it is down. So we have 2, 3, and 4. And again, the OH is on the right side, so the OH will be placed down. Looking at position 3, if the OH is on the left side, it is placed up. The OH at position 3 for D-galactose is on the left side, so it also will be placed up. Here's where we see a difference. On position 4 for D-glucose, it is on the right side for OH, and if it's at position 4 and it's right, it is down. And so we look at the D-galactose, and at position 4, the OH is on the left side. So that is different. So we have to draw our OH going up. Okay, now I filled in the rest, so really it's just those differences between positions 2, 3, and 4 that are going to make the difference for each monomer, or each monosaccharide. And so what we see here is B, so beta D galactose has been drawn. Okay, so like I said, if you know how to draw your glucose, you know your Fisher projection for your glucose, and you know how to draw the Haworth projection for it, you should be able to draw all other Haworth projections from the Fisher projection of other monosaccharides.